Hi, this is Tony Northrup for TrainSignal, and in this video lesson, we're going to cover the Information Communication Technology Infrastructure Basics for the SSCP certification exam. So this is going to be cool stuff like different network components, routers, switches, firewalls, and how to scan your network and find out what's actually out there. First up, let's go over the most common network components. Here's a real typical server data center network diagram. So if you run a corporation and you have file servers and database servers, this is pretty much what your network will look like. There's almost always an internet connection, which we see over there on the left. And the way you connect to the internet is through an internet service provider. And that ISP will give you a physical connection, a wire, and you plug that wire into a router that you typically own. The router, as its name implies, routes traffic between different networks. So in this particular example, it would be routing traffic from the internal network where the servers live to the public internet and back and forth. So if people need to access your web server, it would go to the router and the router would look at each packet and say, okay, this is destined for the internal network. I'm going to go ahead and forward it on so that server can get it. Inside the router, you'll usually find a firewall, and the firewall is responsible for inspecting each packet further. So the router really just checks the address and the header of the IP packet to see if it really is destined for the internal network. And if it has multiple networks connected to it, which of those networks it should send the packet to. So it just forwards it on. If it gets a packet that's not destined for any of the networks, it might think it was spoofed and decide to drop it. But routing capabilities themselves don't really imply having any security features. The firewall is the security component. Different types of firewalls do different levels of security, and we'll cover that in more detail later. But at the most basic, they'll look at each packet and just see if it might present some sort of risk. Maybe it looks like a ping attack, or maybe they think it's been spoofed, or maybe it's trying to access an illegal URL on your web server. And if it matches any of those criteria, well, the firewall might decide just to block the packet. The next component, the switch, exists on the local area network part of the network, and it forwards packets to individual computers. So these computers are connected directly into a switch. And the switch generally is smart enough to forward a particular packet, or frame as it's called on a local area network, only to the computer that it's destined for. Now, I've not tried to list every single component that you might find on a network. These are just the common components that almost every network has. And I'll also point out that the router and firewall are often combined into a single device, though not always. Many corporate networks will also have more than one of these at each level, so they might have two routers to provide redundancy in case one of them fails, and they'll typically have an array of switches, however many switches they need to connect every single device they have on their network. This is what a typical client network diagram looks like. So if you had an office where everybody had, their own personal desks and they needed access to internet resources and the internet, this is probably how they'd be connected. Of course, just like the servers, we have the internet and then a router. And there's also a firewall that separates the computers from the internet, just like with servers. One key difference here is that the firewall will also have network address translation features. So NAT translates the private IP addresses used by the clients on the right side of the diagram to one or two public IP addresses that can access the internet. I don't think you need to understand the details of network address translation for the SSCP certification exam, but in brief, there simply aren't enough IP addresses for every computer and phone and device in the world to have its own IP address. So what network address translation does is it assigns these IP addresses that are reused. Every company uses the same set of IP addresses. They usually look like 192.168 something or 10. something. There are a few different ranges. And they use these same IP addresses over and over and over again. And the firewall with NAT will use a single public IP address that's been assigned to the organization and initiate all outbound connections using that one IP address. So it reduces the number of IP addresses that you need, and it also provides some security by helping to ensure that all traffic is routed through that firewall. Just like with the servers, the switch there provides communications between the different devices and the firewall, or just between any two computers on the same network. So let's talk about what routers do. Routers are these devices that were invented in the late 60s as part of a DARPA's initiative that eventually became the Internet. And they take a look at the header in each incoming packet and decide which network it should be forwarded to. The simplest types of routers only have two connections, one going to the Internet and one going to an internal network. And I bet if you look at the router that you have for your home internet connection, it's like that. It probably just has what is probably labeled WAN for wide area network and LAN for local area network. You connect the WAN to your ISP's internet connection, and you connect the LAN to your wireless access point or your switch or whatever it is that you have your home PCs connected to. However, in enterprise networks, routing could be much more complex, and many enterprises have hundreds of different local area networks. And there are routers that can connect directly to hundreds of different networks. But more typically, smaller routers will be connected together in a tree architecture like this diagram shows here. The routers communicate to each other using routing protocols to tell the other routers that they have access to particular networks. So in this diagram, this router up here would tell both of these routers that it has access to the entire internet. So if somebody on the internal network 1 here has a packet that's destined for an IP address that isn't on the internal network, well, this router will forward the packets to this router. And then this router will examine the packets and say, well, this is destined for the internet. Routers also handle internal communications. So if internal network 1 here is populated by client devices and internal network 2 here is populated by servers, well, this router is going to send a list of all the IP addresses that it has on internal network 2 over to internal network 1. And then when any client on this network accesses an IP address on this network, this router knows that it can send those communications directly to this router to be forwarded on. In this way, routers both join networks and separate networks. This is called network segmentation. They prevent hosts on internal network 1 from directly accessing hosts on internal network 2. Of course, the two networks can still communicate, but all these packets have to be approved by the router. This allows administrators to set up rules that might selectively drop packets and limit communications between different networks. So routers are a point of control for administrators, and that's what we mean when we say that they segment networks. Routers often have firewall capabilities built in, and it varies from very simple, simply dropping packets destined for a specific IP address, to very complex, and maybe even determine whether a specific host or port on the router is allowed to access a server on a remote network and drop the packets if they're not authorized. Routers can come in either hardware or software forms. The hardware form is just a piece of equipment that you would plug directly into the network, and of course it'll have some sort of software on it, it'll have some firmware that can be updated, but it doesn't necessarily run a full-fledged operating system like Windows. You can also get software-based routers, but nobody really uses these. Software routers are primarily for lab environments and testing, but you can turn any version of Windows pretty much into a router. Just stick a couple of network adapters in it, and it'll route packets just as capable as just about any router. And it'll route packets just like any hardware-based router would. Now, the SSCP exam isn't going to ask you to know the specifics of configuring routers, but I do want to give you a couple of best practices. First, configure your router to prevent unauthorized modifications to the routing tables. By default, many routers will just listen for announcements from other routers telling them where traffic should go. Unfortunately, this opens you up to a man-in-the-middle attack. If another router can tell you that the entire internet is accessible through it and the router starts sending all the traffic to that router, well, this allows somebody with control over that remote router to monitor all of your traffic. So you really want to lock down your routers and prevent automatic routing configurations. Of course, with your hardware-based routers, you should change the default password. Often they come with really simple passwords, and in the case, especially of a home router where you simply plug in 2 cables and it's ready to go, you might never have to log into the configuration tools, in which case you would never have a reason to change the password, right? Well, somebody else, somebody malicious, could take the time to log into your configuration tools and do whatever they wanted to it, including configuring it to route all of your traffic through their man-in-the-middle attack. And finally, even with hardware-based routers, you need to keep them patched and updated. I guess it's really patched and updated mean the same thing, but I want to say it twice because that's how important it is. Keep them both patched and updated. Just like any Windows computer, the router manufacturer is going to be releasing updates as new vulnerabilities are discovered, and if you don't apply those updates, well, your router can get hacked. So let's talk more about what a switch does. Now, I'm an old guy, and back in the olden days, we used to use hubs, and hubs did basically the same thing as a switch. One key difference between a switch and a hub is that you can plug 5 computers into a hub, and the hub is really dumb. If computer 1 talks to computer 2, well, the hub just repeats the conversation to every port. So if computer 1 talks to computer 2, computers 3, 4, and 5 also hear the whole conversation. And this makes sniffing really easy to do because you can just start listening to the communications and know every password that's sent on the network. So switches are a little bit smarter. They switch traffic almost like a router does, except on a local area network. They look at the MAC address that's in the Ethernet frames. Frames are basically an envelope that contains a single packet. And they only forward traffic to the specific host that's destined to receive it. So if computer 1 sends a message to computer 2, only computer 2 sees it. Computers 3, 4, and 5 don't have the opportunity to sniff unless an administrator goes in and configures the switch specifically to allow monitoring those communications. Switches can also be configured to host more than one virtual local area network, or a VLAN. With a VLAN, you could have a single network for hosts 1, 2, and 3, and a separate VLAN for hosts 4 and 5. So hosts 4 and 5 would be able to communicate directly, and hosts 1, 2, and 3 would be able to communicate directly. But if host 1 wanted to talk to host 5, it would need to go through a router, because, again, routers connect different local area networks. So basically, a VLAN allows a switch to act like multiple physical different switches. Modern switches also have the ability to authenticate computers that are connecting to the physical network using a protocol called 802.1x. Now, don't confuse this with like 802.11, the wireless network standards, even though it does have some similarities. 802.1x basically doesn't allow a host to communicate on the network until it's provided some sort of authentication. And the switch itself isn't really smart enough to figure out your username and password, but you can configure the switch to talk to typically a radius server, and the radius server can then talk to your Active Directory domain controller or whatever system you're using for single sign-on authentication. You can use this type of authentication system to even verify the health of hosts that are connecting to the switch. So you can plug a computer in and then require the host to run some health checks on it and make sure that the malware software is up to date. And if it's not, well, the host will get connected to a quarantine network where they can download the latest updates and get information about how to contact IT. If the host does pass the health check, well, they get connected to the full network and they can access the rest of the internet. Firewalls separate network and examine every packet being transferred between those two networks. Firewalls only forward approved packets. By default, they'll drop every single packet that comes through. So you have to enable some rules for the firewall to forward any traffic at all. As I discussed earlier, one of the most common firewall features is network address translation. Another feature is to create a demilitarized zone, also known as a screened subnet. A demilitarized zone is just a separate local area network that carries public resources like a web server or an email server or a file server that might need to be accessed from the internet. So you can keep your clients on a private network that doesn't accept any incoming connections from the internet, and then put your servers over in a demilitarized zone so people can access them from the internet. Obviously, the DMZ is more likely to be attacked by hosts on the internet, but it's a risk you have to accept if you want to allow some internet access. Firewalls can be either hardware-based or software-based, also known as host-based. Nowadays, most firewalls are hardware-based, though people do still use Windows and Linux PCs as firewalls because they can provide a great deal of intelligence and complexity. Here are some firewall best practices. Obviously, you want to be sure to filter both inbound and outbound communications. Firewalls will typically have very restrictive rules by default, and you'll have to go in and configure them to allow anything through at all. Keep these rules as restrictive as possible. Now, when I say both inbound and outbound communications, well, For client networks, obviously all inbound communication is dropped by default, but you also want to filter some outbound communication. Think BitTorrent and other peer-to-peer file services. You might even want to block your users from visiting specific websites. Firewalls can do this much more effectively and reliably than any sort of host-based software you might install on individual computers. It's a good idea to put firewalls between different departments and networks, especially if there are different security levels. So in a military organization, you might have a firewall between the classified and unclassified networks, or between the classified and the top secret networks, though realistically, military organizations don't trust a firewall to connect those two networks. They trust only an air gap to connect the two networks. In other words, there is literally air between the networks. There's no physical connection between the two networks. So in military organizations, they will simply maintain completely physically separate networks that never get bridged. And finally, just as with every other device, got to keep it both patched and updated. So important, I'll tell you twice. The simplest type of firewall is a packet filtering firewall, commonly called a stateful firewall. Now, back in the old days, we had stateless firewalls, and it's only in contrast to this very simple type of stateless firewall that the term stateful firewall makes any sense. But nowadays, every firewall is at least a stateful firewall. A stateful firewall just means it has a little bit of memory, and it keeps track of every outgoing connection, so it knows which incoming connections to allow in. You know, back in the 90s, we had stateless firewalls because they literally couldn't put, say, a megabyte of RAM in a device to keep track of a few hundred different outgoing connections. So it had to just kind of take its best guess and forward traffic. The simplest packet filtering firewalls simply filter packets based on their header information, which includes the source IP address, the destination IP address, and then typically the destination port number for client-to-server connections. The source and destination IP addresses obviously identify the source and destination hosts uniquely on the internet. The port number identifies the individual application. For example, port 80 is typically used for web communications. It's used for HTTP. If you connect to a secure server with HTTPS, it'll be using TCP port 443. If you use Telnet, it's port 23, and so most applications have their own unique port number, though I've noticed in recent years applications are all just using HTTP. So everything has decided just to use this single protocol, HTTP, no matter what the application is, and this really reduces the value of our packet filtering firewalls. Packet filtering firewalls, by definition, don't look at the payload of the packets. They don't look at the contents. So they could tell that you're communicating on port 80 and take a guess that it's going to be web communications, but they don't know the URL of the website that you're visiting, or what page you're downloading, or what type of content is in there. The good thing about packet filtering firewalls is they are cheap. They are ubiquitous, in fact. You can buy a $20 router for your home and it'll have a perfectly capable packet filtering firewall. They're also really fast because they don't have to do a lot of thinking about every packet. In other words, they don't have to process the contents of the packet. It doesn't take a high-powered CPU or anything. They just transfer the packets at what they call wire speed. It just goes from one circuit right over to the next one electronically with almost no latency. The weaknesses is that they're dumb. And as I was saying, every application nowadays just uses HTTP. So packet filtering firewalls literally can't tell the difference between AOL Instant Messenger and web communications because they both use the same protocol, HTTP. Application layer firewalls are much more capable and expensive. They look at the contents of packets, what they call the payload of the packets. So in the example of web communications, they could examine the URL of the page that you were visiting. So they would know specifically what product you were shopping for at Amazon, or whether you were going to your company's Facebook page or your personal Facebook page. Based on that information, they could choose to accept or deny your request. So you could configure an application layer firewall to let people visit the company Facebook page, but not let them log in under their own personal account, if that's what you wanted. In fact, you could filter any website, or you could reject content that had certain keywords in it. Based on that, application layer firewalls are really, really powerful. Application layer firewalls are often put in front of server data centers, specifically to provide some additional protection. So, for example, in front of a web server, an application layer firewall could look at every incoming request and take its best guess to determine whether it's a legit request or possibly an attack. So if it detected a SQL injection attack contained in the request that was being sent to the web server, it could drop that packet. Now, maybe the web server doesn't need that protection. Maybe the web server would have known to drop it anyway. But application layer firewalls can provide some belt and suspender type protection. Application layer firewalls can even examine web services requests and database requests. So you could say that a particular table in the database isn't allowed to be queried by anybody on the internet. And the firewall could enforce that while still allowing other database queries through. So the strengths of application layer firewalls are that they can filter content and they can also audit usage of different apps based on the rules that you set up. So you might want to allow people to visit their own Facebook page, but just add an event to a log that keeps track of how many times they do it. Application layer firewalls can do that. Their weaknesses are, of course, they're more expensive. Does more, makes sense that it's more expensive, right? And also because they have to process the contents of the packets, well, that's a whole lot more data to look at. Thousands of times more data than just looking at the headers in the individual packets. And that means they require a lot more processing time, and they tend to be a lot slower as well. Now let's talk about host-based firewalls. Host-based firewalls run on individual PCs and devices like smartphones. Just about every modern operating system has host-based firewalls built in. I can't think of one that doesn't. Windows has had it for many years, certainly since Windows 2000, but I think even before then. Because the host-based firewall has access to all of your PC's resources, well, it can do just about anything. It's capable of some really complex filtering. In recent versions of Windows, you can enable a feature called Family Safety. It's designed to keep your kids off of bad sites on the internet, but it's very capable, and it can check every URL that your kid visits against a list of known malware sites, and it can also see if they're typing in dirty words or something. A couple of examples of these features are Internet Explorer's Smart Screen Filter, which in Windows 8 will even help with other browsers besides Internet Explorer, and McAfee Site Advisor. One advantage of host-based firewalls is that the content inspection can actually be a lot more powerful because it's running on the host itself. So one of the challenges that we have with modern networking is that everything happens through HTTP. And in fact, most new applications are using secure HTTP, HTTPS, which is encrypted. And because it's encrypted, that means that your network-based firewall can't inspect the individual packets. But those packets have to be decrypted somewhere, and they're typically decrypted on the host itself. Therefore, host-based firewalls can inspect the contents of packets that are encrypted and provide some additional protection that isn't available on a network-based firewall. This also includes the ability to check for malware. So a host-based firewall can literally check the files that you're downloading. And if you downloaded an executable file, which is pretending to be a Word file, it could in theory warn you and maybe save you from getting that infection. Load balancers are a common presence on data center networks where they have lots of servers. And as the diagram there shows, what a load balancer does is it accepts requests from a client and then distributes it across multiple different servers. So any request from any single client probably goes to a single server. For example, if I log in to visit Microsoft.com, well, their load balancer will receive my request and send me over to server number 1. Now, if you go and visit Microsoft.com, their load balancer will receive your request and say, hey, server 1 just got a request, so let's send this to server 2. And then if Mary visits, she might get sent to server 3. In this way, it allows the web servers to scale beyond what a single web server could possibly provide. Even though it's working with a single IP address and it appears to be a single website, it's indeed backed by many different servers, could be hundreds or thousands of different servers. Load balancing equipment also provides for failover, which is a way to ensure availability. The load balancer can say, hey, I noticed web server 1 isn't responding to any of the requests I'm sending. I'm going to take it out of the pool. And instead of sending a request to web server 1, I'm just going to distribute them across all the remaining servers. So an admin, if they need to install an update, well, they can just take the web server offline, and the load balancing device will just keep sending requests to the remaining servers. Then after they're done with the update, they put it back online and the load balancer determines that it's working again and it puts it back in the pool. So not only does it prevent the website from going down if there's a hardware failure, but it gives administrators the ability to apply updates and take things offline for maintenance during the middle of the day. So that's nice, right? You as the IT guy don't have to get up at 3 a.m. on a Saturday like I used to, thanks to these load balancers. Load balancers often have application layer firewall capabilities. This allows them to, say, inspect the URL that a user is requesting and then send it to a different server. For example, a different server handles Microsoft.com/technet, as does handles Microsoft.com/MSDN, simply because they have a ton of content and they don't need one server to host their entire massive website. So they can kind of slice and dice their website and put it on different servers, and the load balancer can inspect the packets and forward the requests intelligently. Load balancers come in both hardware and software-based forms, so you can run a load balancer inside of Windows or Linux, or you can buy a hardware-based device that you just plug in and configure using web-based tools. Now let's talk about virtual private network gateways. These are VPNs. And a VPN creates a private connection across the public internet. So as you imagine, if you're going to connect to your internet and download confidential documents, well, you don't want that going in clear text across the whole internet, right? Because the internet's a big thing, but it's owned by lots of different companies, and you probably don't trust the network administrators at your ISP and your company's ISP and any ISPs that might carry traffic between you two. So you want everything to be encrypted, of course. And that's what a VPN does. It encrypts it and it tunnels it. VPNs also allow you to access the private IP addresses on an internet, even if they wouldn't normally be accessible from the public internet. So you can connect to this entire private network using this single virtual connection. VPNs provide authentication, of course. They make you type a username and password. They provide authorization, so if your credentials are valid, they'll make sure that you're an authorized user of the VPN, that you're just allowed to connect remotely. They provide accounting by tracking how often people connect and how long they stay connected for. That's useful if there's some sort of bill that needs to be sent, if somebody has to pay for that service. And of course, as I mentioned, they provide encryption. The encryption keeps other people from snooping on your traffic. VPNs nowadays are usually hardware, but back in the day, software-based VPNs were really common just because the hardware-based ones were kind of expensive, and so you might want to use your web server as a VPN server also, just to save yourself a few bucks. This diagram shows how a typical VPN is connected. The VPNs are typically behind the firewall. This allows the firewall to filter incoming requests and identify those valid requests before sending them to the VPN. The VPN terminates the client's connection across the internet and sends those packets back onto the network. Sometimes VPNs are on their own separate network. Sometimes they're just in the same network with all the resources and servers that users might want to access. Now let's talk about one of the coolest things, an intrusion detection system. I'm only going to scratch the surface of IDS here because I'm going to cover it more in a later lesson. An intrusion detection system monitors the traffic on a network and looks for suspicious activity. And IDS can detect suspicious activity by just watching for general patterns or looking for specific phrases that might indicate that a known malware app is running on the network. And of course, if the IDS finds something, it doesn't just sit there quietly, it doesn't keep it a secret. No, it sends an alert, it sends a message off to administrators to say, hey, I see something going on here, you might want to take a look at it, you might want to shut this particular host down because it's sending out a bunch of bad traffic. Intrusion detection systems come in both hardware and software-based forms, as do most networking equipment. The software-based ones are actually pretty common because intrusion detection is such a complex service that it helps to allow it to run inside a full operating system. Now let's talk about security discovery. Security discovery is the process of finding everything that lives on your network. And I know you're thinking, I know what's on my network, of course, but you really don't. People will just come and they'll just plug random stuff in. You'll get some inventive guy in accounting who wants to host his own little server because he finds it useful and he'll plug it in. And you know what? It's not managed, it's going to be a problem. So on a regular basis, you need to just poke around your own network and find out what's out there. Here's what you're going to find. You're going to find all sorts of hosts. And the word host could refer to anything. It could be a router, it could be a smartphone, it could be a PC. You'll find devices like switches and hubs. You'll be able to identify different operating systems. So you can use a network scanner to determine whether it's a Windows 7 box or Windows 8 box or a Mac or a Linux or a smartphone. You can also identify individual apps that are running on the network by examining the network traffic. You can, of course, know if there's a web server running, but you can also know if there's instant messaging or video streaming going on. You could probably even determine if people are watching YouTube videos all day and stealing all your bandwidth. It's also common to look for Wi-Fi hotspots, which we'll discuss a little bit more later. As part of the security discovery process, you want to identify all the hosts that are on your network just to make sure that they're managed, protected, and patched. When I say managed, I mean that somebody's taking care of them. And in addition to making sure that they're protected and patched, managed means that they're meeting your corporate security requirements. So somebody's defined every security setting that needs to be set on it, and it's meeting up with your regulatory requirements and protecting the privacy of the data on your network, and it's as available as it needs to be. In other words, if there was something that you didn't know about but users came to rely on it, what happens when it fails? Well, everybody's upset, but nobody knows how to fix it because they didn't know it existed, and that has actually happened to me. I've had users call me to complain and say, hey, this and this is down, and I'll say, I have never heard of that, we have no record of that. And they'll be like, well, I still need it. So the security discovery process allows you to find those rogue devices. Even if you don't get them off your network, maybe just learn to take care of them. The classic way of doing this is just by using a port scanner. And a port scanner just sends out communications to every packet on your network, and it says, hey, is anybody listening? So a typical port scanner will contact every possible IP address on your network. So if you use the 192.168.5.x network, it'll start with 192.168.5.1, 192.168.5.2, and continue through .255. For every IP address, it'll probably scan every single port number, or at least every well-known port number. So it'll send an attempted communication out to port number 1, port number 2, and then maybe when it gets to port 80, which web servers use, it'll get a response. And then when it hears back, it'll make a note. Okay, IP address 192.168.5.1 is running a web server on port 80. It can even examine the ports in a little more detail and possibly determine what type of web server software is running or what operating system is running. There's a bunch of different port scanners on the internet. You can get many of them for free. There's some pay ones out there too, but just search. The most popular are Nmap and Zenmap. Nmap is a command line based port scanner, and Zenmap is simply a graphical user interface that sits on top of the Nmap capabilities. Another popular one is Angry IP. Now let's take a quick look at what Zenmap can do by scanning my own home network. So I've downloaded and installed Zenmap, which is the user interface for the Nmap command line tool. And I'll just specify the target, which is going to be the IP address range of my local area network. So I know that my IP address range is 192.168.2.1, and I'll go ahead and scan the entire network, which would go through 254. So notice the format here, I just put a dash in. This is my range from 1 to 254. So it'll scan 192.168.2.1, .2.3, all the way to 254. And I'll just do a little bit of a quicker scan, the quick scan rather than the intense scan that's the default. And I'll click the scan button, and it's off and running. Right now it's sending out packets to every possible IP address on my network. It's trying to connect to a bunch of different services. It's probing every router, every wireless access point, every smartphone that's connected to my Wi-Fi networks, everything on my network. And it's compiling this big list of not only what's on the network, but what everything is listening for as far as incoming connections. And whenever possible, it's going to identify the different devices, not just the devices, but the make and model of the network adapters that are connected to them. Well, you can see here that it's created a list of quite a few devices. This is just my home network now, and I have what, like 20 different devices running on it, 15 maybe? Let's take a look at this first one, 192.168.2.1, and let's see what it happens to say about it. Now, you can see there's several different tabs here that show different types of output, and this first one is Nmap Output, the command line tool that's running in the background is called Nmap. So this is just simply the raw output that comes from it. If I select the Ports and Hosts tab here, it'll list every port that this particular device is listening for. So you can see it's accepting connections on 443. Now, I happen to know by convention that the .1 IP address is typically taken by the network's default router. And most routers accept incoming connections to be managed by a web browser on port 443. So this makes sense to me. I can browse over to the Host Details tab here, and it tells me a little bit more about the host. It says that it's up and running and that it's listening on one port and that the other 99 ports that it checked were filtered. Here you can see the MAC address, which is the address that uniquely identifies the router's network adapter. It's got a little safe icon here, which means that Nmap thinks it's pretty secure. The Scans tab simply shows you the specifics of the scan that you last ran. And the Topology tab just makes a little map for you showing all the different devices on your network and how secure they are. The green means pretty secure, and the yellow means not as secure, and the red, of course, is bad news. So let's take a look at some of these other hosts. This host is only listening on port 80. Whoa, all right. The host at IP address 2.4 is listening for incoming file connections using all these different protocols. And it seems that it might not be as secure as some of the others. You can see that it's got a picture of Swiss cheese here, which means it could be bad news. It doesn't necessarily mean it's going to be hacked. This is an internal network after all. But this is definitely something that you should take a look at. I'm going to guess that the host at IP address 2.5 is a printer, since it's listening for incoming printers and it has the protocol JetDirect supported. I'm scanning through the next couple of hosts to find something a little more interesting. Whoa, here's a busy fella. Why does it have so many different services running? Well, it happens to be that this is the IP address of the local host. And of course, Windows Firewall, which is protecting this computer, doesn't protect it from connections coming from itself. So Nmap scanned itself and found a bunch of incoming connections, but a host running on another IP address wouldn't have access to all of those services. Now, I happen to know that 2.207 is a server that I have running on the network, and you can see that Nmap did a good job of scanning every service that's running on it. You can see that this service is identified. See, it says SQL there. That's SQL. That's a database protocol, and it does typically use TCP port 1433. And it's right. I have a database server running on that server. You can also see that a web service is running there. NetBIOS here is a file sharing protocol, as with and Microsoft DS there is Microsoft Directory Services. If you click the Services button here, you can see all the different services that are running on your network and which hosts are running them. So I click Services and then I click HTTP, and it gives me a quick rundown of every IP address on my network that is running some form of web server. And you can see I have quite a few web servers running on my network, but I bet most of you do too, because every device you have running pretty much listens for connections as a web server to allow you to configure it. Now let's talk about protocol analyzers, also known as Sniffers. And these are one of the coolest network tools a security guy will get to play with. Sniffers listen for network traffic and they interpret it for you. They basically show you the contents of the packets, and they do it in a pretty smart way. So most modern protocol analyzers / sniffers will be able to look inside HTTP packets and just show you the URL, so you don't have to dig through all the data there. They can even show you the contents of the web page. They're pretty smart that way. So besides just snooping on your coworkers, protocol analyzers are useful for determining how much of different types of communications are happening on your network. So you can easily determine that 80% of your bandwidth is going to web requests, while 10% of your bandwidth is going to some MP3 streaming or something different. You can also find unusual protocols that you don't allow on the network, and allow you to track down the source and destination IP address and maybe get that off your network, or decide that you want to allow it. If there is an attack on your network, you can use a sniffer to actually capture and record the traffic, so that later on you can examine it and determine exactly how the attack is being carried out and what data might have been compromised as part of the attack. You can configure sniffers to not just capture everything on the network, but just capture communications between a specific host or communications of a particular protocol. This is important because there's a lot of junk on your network. The signal-to-noise ratio is not good, so you always want to filter your protocol analyzer before you start recording. Now, protocol analyzers come in many different forms, and for me, my favorite is just to run a sniffing software on a PC, and I'll show you an example of that later. Another option is to use a hardware-based sniffer that will have Wi-Fi capabilities and probably an Ethernet jack in it, and you can plug it right in, and it's its own little hardware device that does all the scanning. There are even iPhone apps that are capable with the proper adapter of doing this. Of course, before a sniffer can work, it has to be able to receive all the network communications. With a wireless network, this can be pretty easy. With a wired network, it can be a little more difficult because modern-day switches don't simply repeat traffic from everybody to every port. However, switches will almost always have a feature where you can turn on what they call port mirroring or port monitoring, and they will repeat all the traffic or the traffic from specific ports to that monitoring port. This is basically specifically to be used by protocol analyzers. Some switches will even have a dedicated port to be used just for monitoring purposes. A couple of the more popular software-based protocol analyzers are Network Monitor, which Microsoft makes and gives away free to run on the Windows operating system, or Wireshark, which you can run on Windows or OS X. Now let's fire up Network Monitor and take a look at some of the communications on my own network. This is Microsoft Network Monitor 3.4, a protocol analyzer, aka a sniffer, and it's completely free, it's great, it's for Windows, and it's super smart. Happens to be my favorite protocol analyzer. Now, the certification exam isn't going to test your knowledge of the specific buttons or menu items or anything else. I'm just doing this to show you what protocol analyzers can do. My first step here is going to be to click the New Capture button. This creates a new capture, and then before it actually records, I need to click Start. So I'm going to click Start and then flip over to my web browser and issue a web request. And I'm going to try to do this as quickly as possible because there's a lot of junk on every network, and the more junk I capture, the harder it is for me to find what I'm actually looking for. So clicking Start to record, and then I will flip over to my web browser, and I'll visit my web page because I know that I use really simple HTML on my web page, and other web pages have a lot more complex content that can be more difficult to interpret. All right, so there's my web page. Now I'll flip back to Network Monitor and stop the recording. And now I can analyze the packets that I just captured. There's still a lot of junk in there, so I'm going to load a filter which will show me just HTTP traffic. So this filter, you can see, filters by TCP port 80, which is the default used by HTTP. So I'll click Apply, and that'll filter out everything that's not HTTP traffic. Scrolling down, I can find my request to the web server here. You can see it just get slash, and anytime you request a default page for a website, it just comes across as a slash. That means the root page. And somewhere a little bit farther down, we will find the response. There we go. HTTP response, status OK. Now, in this pane on the right, we can see all the details of the packet. That's literally every byte that's in the packet. That can be a little hard to read if you're not a computer. So it's easier to interpret if we scroll over here and expand the HTTP part of the packet. You can see this top part shows us the protocol that it's talking, HTTP 1.0. The status code is 200, which means OK. That just means the server is able to return a response. And then you can see a bunch of information about the packet itself, that it's using IAS6 that uniquely identifies the server. I know that's old, but hey, if it ain't broke. So I'll expand the payload part of the packet here, and here we can actually examine the contents of the web page. I'll just scroll this over a little bit so we can see some more detail. But you can see that this is the actual HTML that I personally wrote as the contents of the web page. Now, this is pretty harmless, just identifies the title of the page. This is just the header information. But if you were snooping on somebody else, you could have some pretty scary contents of it. Let's look at some of the other packets and maybe we can see more. Okay, so here we can just see some of the HTML pointing to some pictures of large whirligig beetles and such. Hopefully this gives you some idea of how powerful protocol analyzers are and what you can use them for. Up last, I'd like to talk about scanning for Wi-Fi hotspots. You have to scan your network every now and then and make sure some jerk hasn't plugged in a wireless access point into your network. If they were to plug in their own wireless access point, well, that would let somebody in the parking lot bypass all of your security and get right into your network, and people do this. You know why? Because maybe they don't like your wireless access point that you've set up for them, or maybe you don't provide a wireless access point, or maybe they don't remember the password. And it's so easy to just get a wireless access point from any retailer and plug it in and get your own wireless network. Well, people do it all the time. They'll just plug it into their cubicle or in their office. And you know what you got to do? You got to walk around with a Wi-Fi scanner and find it. And you do that thing that you see in movies where you keep walking towards where the signal is the strongest until you narrow it down to a specific area, and then you're searching around looking for power outlets and Ethernet cables, trying to find out exactly where this unauthorized access point is. Some of the apps that let you do this are NetStumbler or InSitter. SSID is the name that's attached to wireless network, or VI Stumbler. Now, in the lower right corner here, you see a black and white photo of a couple of handsome devils out doing some war driving. War driving is kind of an outdated pastime where we used to scan our neighborhoods for open wireless access points, and sometimes sometimes unethical people might jump onto these unprotected networks so they could use the internet access. I'll also point out that the ethical hacker on the far side there is my boss Miles at Train Signal, putting together some video training courses for you. This is Tony Northrup for Train Signal, and thanks so much for watching this video lesson.